Hello everyone. In this video, we will continue our discussion about the different programming languages. And this time we are going to introduce a new language, which is the Lisp language. So Lisp is going to be our final language that we are going to cover in this course. So let's go over the language itself, who developed the language and why it was created. So the one who developed the language was John McCarthy. He died in 2011. He's considered one of the fathers of AI. He was the one who coined the phrase artificial intelligence in year 1955. He created the Lisp programming language, and it was the AI's favorite programming language. So he created it specifically for things related to artificial intelligence and machine learning. He was a professor at Stanford for many years, and he won the Turing Award in 1971. So Lisp is considered a fifth generation language. We skipped the fourth generation language data, so we're going to skip that. The different paradigms that in general the languages are mostly famous for are we have functional, which is the Lisp, and we're going to see exactly what we mean by functional. There is a logic, which is a Prolog, and object-oriented programming, which is used in C++ and Java, which is a lot of you are more common, and a lot of you have used object-oriented programming and understand a bit about that as well, that paradigm, how it works. So again, as a reminder, Lisp is a fifth generation language, so we are skipping the fourth generation language. So Lisp, how it was created, how it is all started. It started at MIT. In McCarthy at MIT, he was looking into adapting a high-level language. So we have Fortran at that time. It was very famous. So he wanted to adapt that or create something similar in order to use it for artificial intelligence. And that was in year 1956. We know that AI needs to represent relationships among data entities. So there is a lot of data that need to be handled and you want to create relationships. So list and linked list link structures were common and are going to be beneficial to use in that case. So he decided that at the beginning, he wanted to develop a list processing library for Fortran. So he focused on Fortran and he just wanted to create a library for Fortran. He also created some functions, like for example, this if function that we have right here. So it's basically an if function instead of using an if condition, if statement. So he created an if function. So it's more of allowed him to create list processing and conditional statement to be combined together. So this library with the advances and the function that he added to the Fortran language allowed him to adapt it later on to create a totally different language, which is the Lisp language. But he started at the beginning by creating a library for Fortran for Lisp processing to use it specifically for AI. So what do we need? What do we need in our language and what the language really needs? So we want to have recursive list processing functions. Again, we want to process a list of data, and usually that's going to be processed using a recursive way. So we want to have a recursive list processing functions. We want to have a lot of conditional expressions. That's a basic thing. That's a basic thing that was needed in Lisp. So it was first implemented in IBM machine, IBM 704, which is the same machine that we use for Fortran. It became really popular that a lot of universities, a lot of people start adapting the language itself and creating different versions of the language. That was later on combined into creating the Common Lisp, which is the standardized version of the Lisp, because there was multiple versions of Lisp and it needed to be standardized for people to be easily using it. So the one we're going to talk about is the Common Lisp, mostly going to be the Common Lisp. Sometimes some stuff are going to be different, but mostly the version that we are going to cover in our video will cover the Common Lisp. So in this video, we want to go ahead and dig deeper into Lisp structure organization, how the programs in Lisp look like, and how the language itself is structured. So let's have a very simple example for a Lisp program here. Now, when you read the code, it would look pretty hard to understand in the beginning, but once we go and explain the different part of the language, you will be able to better understand it. This way of writing it is called S expression or symbolic expression. There was a plan for Lisp to be written in a like translated into a different way to be very similar to the ALGOL way of writing down programs, but that was not achieved later on. It would just ended up having this S expression or symbolic expression structure. And that is how you're going to find the language, how it is used, how it actually looks like. The central idea for at Lisp, it's basically a function application. And what we mean by that is there are in general two types of language. There are imperative languages and applicative languages. Imperative ones like Fortran, Algol, Pascal, and routing execution from one assignment statement to another. So if you look at it, it's really mostly based on assignment statements. So having assignment statements and the program basically is based on that. So you go from one assignment statement to another assignment statement. Yes, you call functions and stuff like that, but the focus on is using a lot of assignment statement. Applicative languages like Lisp, the whole idea is applying a function to an argument. So you have a function and then you apply that function to a list of arguments, whatever the number of arguments are. But the whole idea is you apply a function to an argument. So you don't need at all control structures because everything is going to be achieved through functions, which is not the case when we covered Fortran and Algol and C. When you study C as well, you're not going to find that this is the way of how things behave in the imperative languages. Also, something else about Lisp, it uses a prefix notation. And what I mean by the prefix notation, when you look at the language itself and when you look at how the operators are structured, you always have the operator comes before the numbers. So this is basically, if you're going to use infix notation, so you're going to say 1 plus 2. If you're going to use prefix notations, you're going to have the plus sign before having the addition of the two numbers. How this is helpful? It's helpful because you can say now plus, and then you can write down a bunch of numbers. And what this means that we're trying to apply the plus operation on all those numbers. So we're trying to add all the numbers together in one line. Now, we have to keep in mind then, if we're using such a prefix notation, then you cannot basically mix the function because of the list structure that we have. So what do we mean by that? In Algol, you can have 1 plus 2, and then you can say minus 3. But in Lisp, you cannot say that because of you have like a list structure here. You have the function that you want to apply coming at the beginning. So you can apply one thing at a time on a bunch of numbers. Now, does this mean that we cannot apply the others? No, we can definitely add minus and other operation as well to the language. The main thing to keep in mind is that the Lisp is a fully parenthesized language, meaning that if we want to add the minus, we want to apply the minus operation between the numbers from here and other number, then we're going to add the minus, and then we're going to add parentheses here, and then add the second argument we want to have. And because of we have parentheses and everything, we don't need to think much about the presence rules because you actually apply it through adding parentheses. You are indicating which operation needs to be performed before another operation. Other things about Lisp. So since we said that there's no really control structures or control statement or conditions as well, everything is done through functions in Lisp. So if we want to have a conditional statement, we want to have if else statement, then in which we would have normally in Algol, that is applied in Lisp as a function. So what this means is we are if we want to create a condition that does this here, so let's look at this one here first, and then we can go back to the Lisp code to make it easier to understand. So we're applying a null operation to x. So we're checking if x is null, then basically you're going to have a value of 0. Else, if x is equal to y, then you're going to call function f of x or apply function f on x. And then else, then you're going to apply function g on y. So let's look back here. So we're saying we have a condition. We're checking for x to be null. If that is the case, then you're going to have the 0. Else, you're gonna check if it's x is equal to y. If that is the case, you're gonna apply function f on value x, and then at the end, if that is not the case, then we're gonna basically apply the function g on, if that is all not happening, then basically you're gonna apply function g on y. So you are breaking it down in terms of functions rather than using if else statements as we usually use. What about if you want to define a new function in Lisp? If you want to define a new function in Lisp, then there is a function that is specifically used for that, which is the define function. So basically defining a function. So we are defining a new function here. That function name is make table. So we are basically defining your function, and then you are specifying what the function takes, and then basically what the function does. And the argument again here, we have the name of the function, which is the make table, and then we have the parameters of the function, which is the text and the table. So these two are the parameters of the function, and then afterwards we have the body of the function. The main thing, if you notice, everything is between parentheses here, so your argument or parameters are between parentheses, and then when we have the body of the function itself, we add parentheses as well here, indicating the beginning of the end, the different part as well. We have it here. One thing to notice about this function, the make table function, if you notice, we are calling the function again inside the function definition. So this is a recursive function, and we're going to talk about this in more details, but I want to bring your attention that recursion is allowed in Lisp, and it is used extensively to perform operations like iterations in regular language, in other languages. So you notice that everything is between parentheses, everything is treated as a list. But why is that? Why in Lisp everything is treated as a list? Because of Lisp focuses on the simplicity principle. And what the simplicity principle indicates is the language should be as simple as possible. There should be a minimum number of concepts with simple rules for their combination. If there is only one basic mechanism in the language is easier to learn, understand, and implement. So that's why everything is between parentheses. Everything is treated as a list of items. You apply function on things. You don't have iterations. You don't have conditions. You don't have different types of things. Everything just a list in Lisp to make things more simple and to follow the simplicity principle. Okay, so what is more about the list? What is our list here and how we can use it? So a list is a data structure, that the main data structure that we actually have in Lisp. Yes, everything in Lisp is a list, and that makes things simple, but that brings the question, is it making it much easier to read or not? So keep the question in mind when we are working with the language, understanding more about it. Do you think it made it easy to understand the language or made it harder to understand and read the language? So the list, now going back to the list contains symbolic data. So we can, for example, assign a text here to have this long text we have to be or not to be. So, and the lists like these can be manipulated like numbers in other language. So they can be compared, concatenated, split, passed to function. You can work with them as how you treat a regular numeric values in other languages. And in Lisp, the list consists of atoms, which are the atoms, how you think about it, are the smallest entity you have. You cannot break it down into something even more, which is similar to you have atoms in chemistry and things like that, if you want to think about it this way. So the list here contains, contains four main atoms, so to, be, or not, and then there are repetitions of those atoms, but the main atoms we have here are mainly foreign atoms. And we have functions in order to manipulate the different atoms we have, but at the end, the list contains atoms. You can also create a list of lists, so you can do that in Lisp as well. So we can have, this is a list. So you see the parentheses here. The parentheses representing a list. This is one list we have here to be or not to be. And then that is the question. This is the second list. So we have two lists inside combined into a bigger list. Programs also represented as list. As you can see, everything is represented in a way of a list. So for example, we're calling here the function make table, and we're sending it to parameters text and nil, and we're using the parentheses indicating and treating it as a list as well. So it can be a list with our and that can be basically a list with atoms, make table, text and nil, which means that they are themselves as strings or characters, or we can treat the make table as a function with two arguments. Now, how do we tell that apart? Because it can be a list of, we can treat these words here as actual words and actual strings, or we can treat them as a function that we want to apply into parameters. How we can tell the difference in Lisp? The difference, we can do it by adding this quotation mark. So basically, quoted lists means we're not applying a function on them. They are basically, we're treating text, and unquoted ones are to be interpreted. And what I mean by that, if you look here at this list we have here, since we did not add the quotation mark at the beginning of this one, the two here is going to be treated as a function. So as if we're applying a function named two in a list of parameters, which is going to generate an error because we don't actually have this function. But at the end, that the two here is treated as a function, and to indicate that this is not a function and this is something else, then basically we add the quotation mark right here and begin at the beginning of our list. So what are the implications then for having everything treated as a list in Python? We said in Lisp, yes, we said that it make the language simple. It make it easier to interpret as well. That makes it easy to interpret the language itself and to interpret the programs. And what we mean by that is we can basically write down a program to write and execute another program. So you can write in Lisp a program to execute another program. And that's very beneficial and useful in artificial intelligence. Now, going back to the question, did this make things simple? Yes, it made it's simple. Is it easy to read and understand? No, it made it actually harder to read and harder to understand as well. So yes, it made it pretty easy to write a program to execute other programs in the Lisp language, but it made it harder to understand now. When you read the program, you find much harder to understand in comparison to other programs and other languages that we studied before. So as I mentioned, Lisp is interpreted language. So what this means that you go through one line at a time. You have an interactive interpreter usually that you work with. You execute one line at a time. You don't really have to have the complete program being compiled, reduced, and linked and other step in the compilation that we talked about before. That is not going to be applied in Lisp because Lisp is an interpreter-based language. So you can enter a command into the interpreter and the system will execute it. And that's similar as well to Python. It's an interpreted languages. If you use Python, you're gonna get more of a sense of what we mean by that as well. One more thing to highlight about the functions, the basic function that we studied, like that I showed you, like the plus function, these are called pure function. And what we mean by pure function in Lisp, it means that the only effect is a computation of a value. So for example, the plus, if we go previously here, the plus is 2, we're adding 2 plus 3, so giving you 5. It didn't really change any variable. It didn't change anything inside the memory. It just give you a result, which is a 5. Okay, so over here. So it give you a result, which is a 5. So it just computed a value and give you that value. But there are other functions called pseudo functions, which has side effects, more like a procedure. So think about it like the sit function here, which mean we are trying to sit to be or not to be. into this text variable here. So the set the value of text to be or not to be, and it returned as well the value to be or not to be. So now the text variable is holding to be or not to be. So it's very important to differentiate between pure function and pseudo function. Pseudo function has side effect. Pure function only does computation of a value, while pseudo function, like the set function, it has a side effect, which is setting the text variable to be equal to be or not to be. So in our previous video, we talked a little bit about how the list is the main data structure in Lisp. So in this video, we will dig deeper into that and discuss the different data structures that exist in Lisp beside the list. So in Lisp, the data structures we still can have primitive data structures like numbers. So we had that before in other languages, and you can apply operations on numbers like plus, minus, times, and equal, and so on. We can have as well non-numeric atoms like strings of characters, and they are used as symbols. And think about it, they are much like the enumerated types in Pascal, and we can apply operation in them like the equal operations. We actually have as well some special atoms as well in Lisp, like the T representing the true, nil representing false, and also represent other things like non-existent atom, like something doesn't exist, or nil as well is used to represent empty list. So if you get a result that something is true, then you're gonna get the letter T indicating that is true. And if you get the nil, then basically means it's false, or it could also be used if this doesn't exist, or if we want to represent an empty list, and we're going to have more example about that as well. So the list we have is considered as the principal data constructor in Lisp, and from the atoms you can use them to construct your list. The list can be empty, so it can have 0, 1, or more element, and that brings us back to the 0-1 infinity principle. So that's an example for the 0-1 infinity principle about how it can have 0, 1, or more. If we want to represent an empty list, so you can use something like this, the empty parentheses, or you can use the word nil to represent as well that we have an empty list. All lists are considered an atomic, means it does not consist of the basic atom item. Like it can be broken down into smaller elements if you want to think about it. So atom is something you cannot break it down anymore, like a number. Think about it this way. But the list is non-atomic because you can still break down the list to the main primitive data that you're actually using inside of it. Okay. But that except for the empty list. The empty list is considered as like an atom because it's an empty list. Okay, so if we say atom this here, so it's a function to check if it's considered as an atom or not. Or atoms 5 is going to return true. But if we give it an atom, it's going to be not an empty list or a list of other empty lists. You see, it's a list of lists. Then in that case, it's going to give you a nil, meaning that no, they are not atoms. They're not atomic. So how about if we want to have a list, how we can access parts of the list? Well, we access part of the list using two main functions, the car function, and this one is pronounced as kodar, okay? Kodar and car. So what the car function does, it allows you to access the first element of the list. So when you say car and apply it on a list to be or not to be, then it's going to give us the 2, okay? Also the same, if we apply car to a list of element, then gonna give us the first element of that list, which is to be, which is a list of 2 elements existing inside our bigger list right here. Okay. So, and it returned 1 element. So whatever the element is, the element can be a list, like in the case here. The element can be just 1 word we have here. It depends on what the first element that exists in the list is. The Kodar one, it accesses the rest of the list without the first element. And this one returns a list. So when say Kodar to be or not to be, so it's going to ignore the 2 and return back be or not to be. And it is a list, so always return Kodar, always return a list. So how then can we select the second element inside our list? Well, we combine car and Qadar in order to be able to do that. So if we say Qadar, then Qadar is going to return us the list after the first element. So it's going to be B or not to be. And then when we apply car on that new list that's returned by Qadar, then we're going to be able to get the word B. How about if we want to get the third element? So we're going to have like the same operation. So we're going to do Qadar first time, going to give us B or not to be. And then we apply it the second time. So going to give us or not to be. And then we apply the car, which is going to give us the first element in that list, which is going to be the or. So basically applying consecutively Qadar gonna give you the list and the car one time gonna give you the first element from that part of the list. So that's gonna allow you to cut the different elements in order to get the element that you are interested in. How about this? How about if we have a list here that includes an employee record? Think about it this way. So we have Don Smith. He's 45 years old. This is his salary, and then this is his hire, the date of hire. So how about if we want to get this part here? So our list here, DS, contains that. So we want to select the date of hire. So we applied the Qadar multiple times, Qadar, 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 and then we apply car to get that part, and then Qadar again, and then car to give us the for. So you see, we applied in a different order in order to get the different part. Yes, confusing, but you can get used to it and understand based on the order and the location of the different things, how you can get the part that you are interested in. So let's look at it again. So the first Qadar is gonna, how about this? Let's clean things a bit here, erase. Okay, and let's do it again. So we're gonna apply that sequence to our list here. So the first time we apply Qadar and DS, that's going to cut it here. Second time to apply Qadar, going to cut it here. Third time we apply Qadar is going to cut it here. And now we have a list remaining. So we're going to call car to get that first element from inside the list to get it out of the list. So you're gonna get August 4 and 80, and then we want to get the 4. Remember that we're gonna get the day itself. So we then apply Qadar again. So we're gonna cut it here, and then we apply car to be able to get the 4. This can also be simplified in the language by just having by basically you notice the difference in the A and the D. So we just have a letter C at the beginning, R at the end, and then you just a sequence of D representing and A is representing that sequence. So that this D here representing first one, this D here representing second one, and so on. So representing the same sequence, we've applied, it's going to give us 4. More of simplification when you're writing it down. And to make it easier, it's really hard to remember that sequence, and you can make a lot of errors as well. So one way of doing it is we can define a new function. We can call this function higher date. That basically applies when the argument are, and then the body of the function is basically applying this sequence of car and Qadar on R to return back the higher date. And then we can create another function day that takes a list as a text as well, D, and then that takes a higher date basically, and from that at the higher date, and then from that we can apply a sequence of Qadar and car in order to get the day out of that higher date. Okay, so now if we want to select the day of the higher date, we just apply day, which is a function on the higher date function that's going to be applied in DS. So that's going to give us the 4. This is more readable and much more maintainable. You can have less errors as well than writing down this whole sequence. If you drop one D or drop one A, that's totally change what you are working with. So if we go back to our list, the Don Smith 45, 3000, August 4, and 80, this is really hard also to maintain and hard to read. Like, yes, we know that this is the name of a person, but we don't know, like, is it the first name Don? It's the last name Don? We don't know what the different part of the of our list, or we don't know what the elements actually mean. And it's hard to change the structure of a list because we don't, that each part is not associated to a specific property, is not a specific to, associated to specific meaning, so hard to change. So a better way of doing this is use something called a property list. And what I mean by that, before every part, we actually add a property to it. Okay, so this way we can search for a property name we want and return the value we want for that age. And the order of the properties become immaterial because we are looking for a specific property that we want to return the value for, not a specific order in the list. We're totally independent of this order of the list. And the general form for that is property one, value one, property two, value two, and so on for all the properties and the different values. Now, how we want to access a specific property then from our list? How do we find the property we're interested in? So if the property we want is the first one, which is basically we want to access the name. So we want to be able to retrieve back Donna Smith. So we basically return the second element of the list because you skip the property name and then you go to Donna Smith. Else skip first two element and start over. Otherwise, if the one we're not interested in, then we're going to skip the first two elements because it's a property and a value associated to it. And then we skip over to the next two values and start to the next part of the list and start over again. So we can define a function, get property P of list L. So we define get property P, we give it the property we're interested in, the list we have. So this is the argument of our function and the implementation of a function. We check. So this is a function. We apply equal to the beginning of our list and we compare it to the property. If this is true, then we're basically going to retrieve back the property we have, the value for the property we're interested in. Otherwise, we're going to call the function again, and this time we're going to remove the first two elements from inside our list, and then we continue working on the remaining part of our list. So you see, it's a recursive function. It's calling itself. We're going to keep doing this until we reach our base case, which is we found the property we are looking for. And instead also of using property list, there's something called association list. And the association list is very beneficial when we have a property that doesn't have a value. So for example, if we have an employee and we have a property for an employee which is retired, but the retired itself doesn't have a value because the employee itself is working. Or if the property itself has more than a single value, then how can we represent it in the property list? So an association list makes it much easier to work with that if that is the case rather than using the property list. And the association list, basically think about it as a list of lists. So basically you're going to have inside our main list, we have a list representing the property and the value associated with the property. A second list representing a second property with the value associated with the property. So if we have a list with a property, but it doesn't have a value to it, is basically it can happen because it has its own part of the list here that makes it different. That makes it easy to understand that we'll reach at the end of this list, that we know that it doesn't have a value. It's a property like retired. It doesn't have a value for that employee yet. So far what we have covered, we're actually breaking down our list. We're taking part of a list. We need something as an inverse to our functions we have here. So our functions car get the first item of a list and codar get rest of list. So we want to have a function that does an inverse thing for this, which is construction, cons here too, which is append first of list to rest of list. So this is more appending two things together. So construction, so we want to append the word to the list here, be or not to be. So we're going to have to be or not to be. And it returns a list, as you can see here. If we give it to be as the first part we want to append to our list that we want to append it to, then you're going to notice here it appended it as a list. So whatever you give it, if you give it a list to add, then it's going to treat it as a list and going to add it as a first element here. And we're going to talk later how we can not do this. Like we want to add to B, we want to add multiple words to the beginning of our list. We just don't want to add one element at a time. We want to have a bunch of elements that we want to add to our list and be treated as part of a list, not being treated as a list inside our main list. We're going to see how we can do that, which is right here. So we want to do appending in a different way. So we want to be able to, when we append to B or not to B, we're going to take to B, and then this is whole one, B1 whole list. So how would we do this? We basically implement the function append itself. And how we can implement the function append, we need to extract and construct the last element of the first list successively. So we can basically use our car and codar functions to help us with that. So we define a function, append, that takes two element, list, and the m, which is we want a list appended to m. If L is null, then basically M is the one that we have. Otherwise, we construct by taking the beginning letter, the beginning part of L, and then appended to the remaining part of our list here, which we again calling append, and append is going to call codar of L and M. So what does this mean? Okay, let's look here. Let's look at our to be or not to be here. So we want to have to be or not to be. We are gonna take B and then add it to our list, and then take the 2 and then add it to our new list, which is be or not to be. So it becomes to be or not to be. Because if we go back to cons here, you're going to notice that if we give it one word, then it will be able to successfully add it inside our list. If we give it a list, then it will take the whole list and add it. And that's what we don't want to have. So we're going to basically break down our first list into smaller parts in order to be able to add to be or not to be, okay? By implementing this out of this recursive function by taking one element at a time from inside our list. So how lists are then represented inside the memory? Like they look very handy. So far you notice they don't really have a length or anything like that. You can keep adding to them. There's no limitation. They're not basically like arrays. They're more like linked lists. They are more represented like a linked list. So to be or not to be, we have our node here that contains 2 and then has a pointer next that points to the word B points to the word or, and so on. And the last node we have here points to nil. This means that there's nothing else that we're having. How about if we're having a list of lists? Okay, which is like a frequency table or a frequency list that tells us the frequency of each word. So we basically have our main list here that the first one is holding 2, 2, and 2. So that's the one here. And the second one is holding B and 2, the second list here. So we have 2 nodes, and this one is our final node right here pointing to null. How then we have a linked list? We have a list represented as a linked list. And a question would arise then, what are the origins of the word car and kudar? How did those names come up in the first place? Well, the first Lisp was designed for the IBM 704, and one word had 2 fields. It had the address field and had the decrement field. So the word car comes from content of address part of register, and kodar is content of the decrement part of the register. So if you look at our linked list here that we have, so car is the first part of our node here, and kodar is basically the pointer which is next that holding the address for all the remaining part of the list. So think about it in terms of a linked list. This is the data or the value part, and this is the next part. So kodar is holding next part, and car is holding the value or the data inside our node from our linked list. Now, in Lisp or the IBM 704, this is called the register. So the content of the address part of the register and the content of the decrement part of the register. So these are, and that's basically the abbreviation for that. So keep that in mind when we're working with car and kodar. So how then if we have a linked list, how then the cons being implemented. So you notice that car and Kudar, they're basically returning a node. They're not changing anything about the linked list. And they're just returning the respective part of the list. So how can we implement the cons? Well, the cons is about the job is constructing a new register using two pointers. So it's trying to add a new register. Think about it as adding a new node to your linked list. So it allocates a memory location and it fill in the left and right part of the new location. So the new location that we have, the registered part, the allocated here, and makes the address register here hold the two, and the second part basically holding the address of the remaining, or points to the remaining part of our list here. So returning back, if you remember how linked list works, if you remember how we constructed and added, this is basically appending a node to the beginning of our linked list. This is our data part, and this is our next part. So we're making our next part holding the address of the remaining list. So you notice that construction, we're adding things to our linked list. So let's say that we have a bunch of instructions that we have here. So we're setting a list L to be holding or not to be. And then we're setting M to the two atom words to be. And then we're setting N to be construction. We're constructing a list from the applying this function here to M and then with to L, and then which is basically going to end up B or not to be. And then we're setting O to by constructing another list as well to be or not to be. So we have or not be, to be or not to be, and then to be or not to be. So when you think about that, you think, okay, we are creating new variables inside the memory. We are reserving different location. These variables are really not connected together, or these lists are really not to get connected together, are not related to each other in memory. Each one has its own location in memory. Well, that is not the case in Lisp. These are considered to be sublists of each other. So they are at the end pointing to the different, like to be or not to be is going to be think about it as one list, and then each different list we have, or each different list is going to be considered as a sublist of the main list. So we have L here starting for or not to be. We're going to have the O starting from to be or not to be. We have the N is starting from be or not to be, and so on. So it's basically, and the M one, it's just ending at to be. So this is a list on its own with its own nodes. Okay, but it's pointing to the same atoms. 2 and B are two atoms existing inside our memory that they are all holding and sharing with O being the main whole list we have here, and L and N are considered as sub-list of the O list. Now that looks pretty cool and pretty nice because we're saving the memory. We're not copying new memory location. And so far it looks safe. It doesn't change any of the nodes. We didn't change anything. We're just adding, constructing new list and appending to new other nodes, but we didn't really do anything wrong to our existing L list, right? Because M is a different list, L is a different list, N is a combination between M and L, and O as well is a combination between M and L. So we're combining, creating sublist, and so on. We didn't really change anything internally in any of the existing lists, so it looks pretty safe. However, one important thing that we want to bring up is list structure, unfortunately, can be modified. So all the function we have covered so far do not modify any of the existing list, as you have seen. Even the construction, it just add new nodes, but the content of the existing list does not change. It's still the same letters, the same words existing in the L list. If you want to look back here at the previous example, when N was constructed from M and L, it basically was constructed from it, but L stayed the same. It did not change. Okay, but we have some function that can create a modification, which is replace an address function. And which is replace the address part, and replace D, which replaces the decrement part. So it's possible that more than one symbol points to a list. However, that causes the issue that it can be modified using these two functions, and that can cause the unexpected problem like the equivalence in Fortran. So if you remember the equivalence problem in Fortran, when two functions using the same memory location, storing the same memory block, one of them can modify the other, that location, and that can affect the other function or treat it differently or using it as a different data types. So it modified without the awareness of the other function and causes a lot of issues. When we had and now in Lisp, when we had our linked list and we had some lists like the L, the O, and like the M, they're sharing using part of those our list we have here. That ends up if we modify one of those lists. Like for example, we have here the O, and the O is using exactly the same memory locations as the L. So if part of the O using the replace A were modified, it's actually going to affect the L list that we have right here, because both O and L points uses the same memory, use the same memory location. So if O changes something, that's gonna affect L, and vice versa. If L changes something, then that's gonna affect O. So we're creating that issue that when multiple variables or multiple list point using the same memory location, when one modified, that's affect the other, and that can create errors. Again, create a lot of security problems as well.